First introduced M.Bassetto, who is from the University of Pisa and will speak to us now about logarithmic spiral trajectories generated by solar sail. I will give you something on 5.
Okay, thank you. Thank you, good afternoon. I'm M.Bassetto, and the work I'm going to present you today is joint with my colleague Lorenzo Nicolai and Professors Alessandro Quarta and Giovanni Mengali from the University of Pisa. This work is about the logarithmic spiral trajectories generated by solar sails. No? Doesn't work.
Is it off?
No, it is off. We don't have to
Forse che scaricare sulla slide non...
working before.
The laser works.
The laser works.
Everything works. We have the receiver on the computer.
But this is...
That's important.
Yes,
Where is it? It's here.
I will
Try to do it again. Oh, I can skip to the next one so you can start speaking. No?
Forse con clic sulla slide. Questo.
Not even. Ah, okay. Please.
But,
Now it works.
okay.
Thank you. So this is the outline of my presentation. First I will introduce our goals, and then I will talk about the main features of solar sails. Then I will describe the mathematical model we have used for the description of one possible application in an heliocentric context. Now, the aim of our work is to analyze the logarithmic spiral trajectories traveled by means of solar sails using two different thrust models, the ideal and the optical one. In particular, the optical thrust model is consistent with the recent result of Heaton and Durbrims of 2015. As regards the mission application, I will describe you a possible heliocentric phasing maneuver. Now, the solar sail exploits the solar radiation pressure to generate thrust. So the solar sail is a propellantless and passive propulsion system. Why passive? Because it doesn't need electrical power to work. The thrust for a solar sail is proportional to the exposed area and scales as the inverse square of the distance from the Sun. Two past missions, NASA NanoSail D2 and JAXA IKAROS, have already provided the feasibility of such propulsion technology. Now, as regards the solar sail propulsive acceleration, we can describe it in a two-dimensional polar reference frame. Here, AR is the radial component of propulsive acceleration, and AT is the transverse one. In particular, here, beta is the so-called lightness parameter, which is the duration between the maximum propulsive acceleration given by perfectly refractive solar sail at a given heliocentric distance, and the local magnitude of the solar gravitational field. Then R and T are two-dimensionless quantities that represent the radial and transverse components of A, respectively. Here you can see that R and T are functions of an angle, alpha, which is defined, which is the pitch angle, and is defined as the angle between the local radial direction in an orbital reference frame and the normal to the sail plane. R and T depend also on three coefficients, V1, V2, and V3, the so-called force coefficient, which depend on the optical properties of the membrane. If you look at this figure again, we can define the thrust angle, which is the angle between the local radial direction again and the direction of A, and the flight path angle, that is of course the angle between the V and the local horizontal line. Now, this is the difference between the two thrust models we have used. In particular, for the ideal force model, phi coincides with alpha, because the surface is perfectly reflective, And while as regards the optical force model, phi that does not coincide with alpha, and it has a maximum value and a minimum value in modulus equal to about 60 degrees, when alpha is about 74 degrees. As regards the dimensionless thrust modulus, the square root of r squared plus t squared, it has a maximum value when alpha is equal to 0 for both cases, but you can see that for an ideal force model, the maximum value is equal to 1, while for an optical one, the maximum value is about 0.9. The solar cell dynamics can be described in polar form in this way, the two-dimensional dynamics, where the angular coordinate theta is measured, as you can see here, from a fixed direction that in our case is the parking orbit eccentricity vector. Now, the hypothesis that we have to make is that r and t are constant, and once that we know the optical properties of the membrane, this implies that alpha and phi must be constant. Now, one possible solution of the equations of motion is the well-known logarithmic spiral, whose equation is given by this expression, where the tangent of gamma, the tangent of the flight path angle, is a constant value. Theta 0 and r 0 are the initial conditions, and in particular, the tangent of the flight path angle is a function of the osculating eccentricity and true anomaly. Now, once that we have the solution, we can derive the osculating orbital parameters, in particular, and their evolution with respect to the angular coordinate theta. In particular, A and P, the semi-major axis and the semi-latus rectum of the osculating orbit, are proportional to R. You can verify that they are proportional to R, because gamma is, of course, constant, while kappa, which is defined as the ratio between the speed, the local speed, and the local circular velocity, here there is a mistake because it is mu sun divided by r, is a constant function because it depends on beta, t, r, and gamma. Okay, so we can conclude that the ratio between p and a, which is a function of gamma and k, is constant. So E must be constant. Moreover, since the tangent of the flight path angle is constant when a spacecraft moves along the logarithmic spiral trajectory, also the osculating true anomaly must be constant. So we have just verified that when a solar sail-based spacecraft moves along a logarithmic spiral trajectory, its osculating eccentricity and its osculating true anomaly are constants of motion. And one important consequence of this statement is that the rotation of the upside that I have indicated as delta omega is equal to the variation of the angular coordinate delta theta. Now, the question is, once that we know the initial conditions in terms of initial eccentricity and true anomaly, what are the thrust requirements in terms of lightness parameter and solar sail pitch angle alpha needed to insert the spacecraft in a logarithmic spiral trajectory and without an impulsive maneuver? Now, from the equations of motion, and according to the definition of gamma and k, it is possible to derive two relationships that relate the pair beta alpha and the pair E0 mu0. And these two relationships are these ones. Note that these two relationships are valid regardless of the adopted thrust model, ideal or optical. At this point, we define a function of E0 and U0, P here, has the ratio between beta t and beta r. Of course, these functions coincides with the tangent of the thrust angle phi. Now, this function of E0 and U0, P, must be equal to f of alpha, where f of alpha, which is a function of only the pitch angle alpha, is defined starting from the definition of T and R that I showed you before. So once that we we have fixed the initial conditions E0 and U0. Alpha is given by the inverse function of f computed in P. Now, at this point, we have to distinguish between the between two possible force models. For the ideal force model, the solution to this equation is unique and analytical, since alpha is simply given by the inverse tangent of P. For an optical force model, instead, there is more than one possible value of alpha that solves this equation. Of course, we are interested in the smallest values, or in the smallest value of alpha, in modulus, of course, because the smaller each angle, the smaller the required lightness parameter. And by interpolation of numerical data, it is possible to approximate alpha in this way. Now that we know alpha for both the possible force models, we can compute beta according to this relationship. Now, are all the initial conditions possible? The answer is no, because we have to comply with the condition r greater than 0. As a matter of fact, the solar sail can provide a negative radial propulsive acceleration. So once that we have enforced this condition, we have to find E0 and U0 such that this expression is lesser than 0. Now, a necessary condition is the osculating parking orbit must be closed. That is to say that it is impossible to move a solar sail-based spacecraft on a logarithmic spiral trajectory if the osculating orbit is open. For closed osculating orbits, instead, not all the pairs E0 and U0 can be selected, however. And on the plane U0, E0, the extension of the feasible region, of course, depends on the adopted force model, as expected. And in particular, for an ideal solar sail, this region is wider. These are finally the results in terms of required lightness parameter and alpha that take into account the operational constraints on the initial conditions. Note that beta quickly grows to plus infinity when the modulus of alpha tends to its maximum value, which is 90 degrees for an ideal solar sail and, as I mentioned before, 74 degrees for an optical solar sail. Now I would like to draw your attention to this figure in particular. You can see that if we consider small values of E0, and if we are sufficiently far from these regions, E0 is a weak function of mu0, and in particular, it is exactly equal to the osculating eccentricity if mu0 is equal to 180 degrees. So the value of the osculating eccentricity gives a rough idea of what the required lightness parameter should be in order to move along a logarithmic spiral trajectory. Note that beta is symmetric with respect to mu0 equal to 180 degrees, while alpha is symmetric with this point, mu0 equal to 180 degrees and 0. To move to a possible mission scenario, we have decided to describe the possibility to perform a phasing maneuver through these trajectories. In particular, a phasing maneuver consists in change the angular position of a spacecraft along a given working orbit. The idea is to split the maneuver into 3 phases. In the first phase, the spacecraft is allowed to move along a first logarithmic spiral arc in which the angular coordinate increases of 180 degrees. And so also the rotation of the apse line is 180 degrees. Then a coasting phase follows, in which of course the only orbital parameter which vary is the true anomaly, and then through a second logarithmic spiral arc, the value of the semi-major axis is brought back to its initial value. Omega, the final value of omega is equal to the initial one, and now Thank you. And now the spacecraft has a different position along the initial working orbit. So the result, the final result, is a phase angle theta that you can see here. Particular, the phase angle theta is the difference between the angular position that the actual angular position of the spacecraft after the maneuver and the final angular position that the spacecraft would have if the motion were perfectly Keplerian. Now, the symmetry of the problem is justified because of the simplicity of the steering law. As a matter of fact, moving along these two spiral arcs, the two required likeness parameters are the same, and simply the attitude of the solar sail must change its sign. So if alpha 1 is the attitude of the solar sail plane during the first spiral arc, the attitude along the second spiral arc must be minus alpha 1, and it is a very interesting result. These are the mission performance of an ideal solar sail-based spacecraft for 3 different values of osculating eccentricity. So here you can see the value of the phase angle as a function of the ratio between the coasting phase semi-major axis and the working orbit semi-major axis. Note that this line corresponds to have beta equal to the osculating eccentricity. In this figure, instead, you can see the mission duration parameterized with respect to the working orbital period as a function of the phase angle. Note that you have a discontinuity in the mission time when nu0 is equal to 180 degrees. To conclude, we have determined the orbital parameters of a solar sail-based spacecraft when it moves along a logarithmic spiral trajectory. Then we have computed the thrust requirements in terms of the likeness parameter and alpha, it is the pitch angle, that allow the spacecraft to insert in such a trajectory and without any discontinuity in the velocity vector. Then, of course, we estimated the constraints on the initial orbital parameters in terms of the initial eccentricity and the true anomaly in order to satisfy the condition that the solar sail can provide a negative radial propulsive acceleration. And then the results for an ideal solar sail have been applied to the analysis of a phasing maneuver. Thank you, and I'm glad to answer your questions.
Thank you very much, and thank you for keeping the time. Are there any questions?
Sorry. During the costing phase, the solar sail is off.
Yes.
Right? So from a practical point of view, you have to...
From a practical point of view, the solar sail attitude is changed in order to have the plane parallel to the sunlight.
Okay, thank you.
All right. If not, let's thank the speaker again and move to the next talk.
Thank you.